Prior to the 1950s, the prevailing wisdom in car design was that strong, rigid-bodied vehicles were safer than weaker ones. It makes intuitive sense. Would you rather drive around in a strong metal shell or a weak metal shell? Stronger is better, of course. And so that's pretty much how automotive design went until a young Hungarian engineer by the name Bela came into the scene. Bela knew that the problem with strong, rigid bodies was they transferred the kinetic energy of crashes straight to the passenger compartment, increasing the chance of injury and death. Humans were in effect the weakest link in the design. What was needed was a way to reduce the kinetic energy reaching the passenger compartment. Bela achieved this by inventing crumble zones, sacrificial zones in the front and rear of the car designed to fail first in a collision, collapsing in a controlled fashion like an accordion and dramatically reducing the energy transfer to the passenger cell. It is an amazing counterintuitive innovation. In 1959, Mercedes-Benz was the first production automobile to feature crumble zones, and they would soon become a standard safety feature in all cars. Crumble zones exemplify the power of the weakest link principle. The weakest link principle is the use of elements in a system designed to fail in order to protect more important elements in that system from harm. Accordingly, a properly designed weakest link in a chain is the most important link. Examples include shear pins in mechanical systems designed to shear off if the load of the system passes a critical threshold, and trading curbs on stock exchanges, which automatically shuts down an exchange in response to a substantial drop in value, or electrical fuses in electrical system designed to melt and break the circuit if a surge of current risks damage equipment. The weakest principle works in two ways: halting or disconnecting systems when they fail, like electrical fuses, or mitigating damage during or after they fail, like a fire suppression system. The principle is applicable to all systems with cascading fault condition. That is when there is a chain of events that can be interrupted. So, how can you apply the weakest link principle? Whenever you are dealing with situations where failures occur as cascading events, which is how most failures occur, by the way, you can look for opportunities in the event chain to insert weak links. For example, people often trip over computer power cords, which pulls on the computer, which can make it fall to the ground, which can cause damage. Apple inserted a weak link in this chain in the form of MagSafe connector, a magnetically attached power connector that detached before the pull of the cord is great enough to move the computer. The MagSafe connector interrupts the cascade before damage to the computer occurs. If you decide to add a weak link to a design, test and verify that link only fails under appropriate predefined conditions. You obviously don't want it failing under regular use, but you want it to reliably fail when conditions warrant. So, whether you apply the weakest link principle to prevent damage to equipment or property, to interrupt group or mob behaviors like stock exchange swings, or to invent the next revolutionary safety innovation, remember, the weakest links can make the strongest chain.